Hi, and welcome to today's webinar on GENOA 3D PTMG module. Today, I would like to show you how GENOA 3D PTMG can help you to to reduce your material qualification process. Here we have GENOA software GUI, and from there we connect to the app launcher, and also from there we can connect to TMG module, as you can see here. And one thing that I would like to mention that the user can use any G code to convert that to CSV format. One of the input required for TMG is CSV, which is basically the coordinate system and the power and speed of the laser in LPBF process and laser-based process, in fact. And also, let's take a look at the input parameters on the right side. This is the TMG input panel. We have process settings, materials, as well as visualization and boundary specification. In the first tab, we have process settings. These are the process parameters for different processes. And the processes that we have so far are as follows, as you can see: LPBF, SLM, DMLS, SLS, FDM, and also BAM. And here is the printing path, which I already mentioned, which is a CSV file that it was converted, based on the G code. And also different parameters such as scan speed and as well as total power can be input in TMG. And as you can see, I consider here a range of power and speed because I would like to show you the process map. And process map is basically it's different TMG calculation for different power and speed cases, which therefore we can come up with the process map and a stable region, and also a void map, which shows you the minimum void predicted by TMG. So let's go to the next tab, and this is the material that user can input their own material system, and these are the parameters that needs to be filled by the user for TMG. And also, if you have multiple material, then you need to repeat this for each material. And also, they can input their properties, or either it is available or they want to use their own library for, in fact, the thermophysical properties, which is temperature dependent. And also for visualization, you can visualize the temperature, density, volume of solid, void, and melt pool size, and other parameters. So let's take a look at the outputs of TMG. So we visualize the TMG outputs from 3D's module. And here we have different TMG modes to visualize. One is process map temperature, process map void, which are our main focus here, and thermal temperature, void, VOS, density, conductivity, as well as conduction, convection, and radiation. So let's start with process map temperature. There are two files here that are basically generated from TMG. One is, in fact, maximum temperature for the process map, and also the process map CSV file. So as you can see here, you have different region of stability and instability based on different power and speed. If I zoom in a little bit, you will see that this is the maximum temperature CSV file, and here what you see is different regions such as not melting, incomplete melting, balling, overheating, clumping, as well as stable region. And what we're really looking for is the stable region in the middle here. And one of these stable region has the minimum voids. Therefore, we need another 3D map to show us which one has the minimum or least void, average void during the 3D printing process. And so before I show you the void map, let's take a look at these values. For example, you can zoom in and show the speed and power case. So here, for example, we had a speed of 300 millimeter per second and power of 260 watt. And this is the maximum temperature predicted by TMG for that specific power and speed. And yeah, so let's go and take a look at the other map. So here as I'm switching this to void map, the input file also automatically switch to minimum void CSV file, which is basically the average of minimum of the uh, basically the calculation from TMG. So here, let's take a look at the coordinates. So here, instead of maximum temperature, we are looking at the void percentage. And here, if I zoom in a little bit, you will see that, for example here, as you can see, we have the maximum void predicted by TMG at this specific situation. That this is the power and speed. And also here, we had a high void predicted by TMG. So the thing is, we are trying to minimize the defects, and one of these defects is basically micro voids. And this is one of the capability of TMG that can be used to minimize the void and find a stable region. So here, if you look at the void value, you will see that this is a 1.4% at this specific condition, which is 800 millimeter per second and 500 watts. But how can we come up with all these maps? Basically, what you need is other parameters that is calculated by TMG, such as the thermal state, which gives you different region. Oh, sorry. So I have to change the file here, browse the input file, and then what you can see is, let's pick one of these binary files of the specific condition. And if you take a look at this, this is just a simple model to show the capability. And as the laser moves, you see that you have different region, from heating to cooling to solidification, superheat, cooling, melting, as well as melt superheated, which is the overheating region. And these are clearly shown by different color. And so what user can do is change this to basically let's see, yeah, let's change the data. So here you are looking at the thermal state, which is really important in calculation of process map and the void map. And also we have the VOS void, temperature, density, conductivity, conduction, convection, and radiation, like I said. So let's change it one by one and see how it shows. And so this is basically volume of solid, which is 1 minus the void, and this is the macro void. You can change it from the full spectrum, which is global range, to current range. And then you can see what is the where is the actual maximum void, and this is basically transient conditions. So you can keep track of changes of each parameters during the process. And also you can take a look at the temperature, and as you can see the heat affected zone, and also you can visualize the and this is also the temperature range. You can see if it is overheated or not melted. And another feature that we also have is to hide the unfused region. So as you can see, this is the powder bed, and the laser only moved so far from this location, from here to there, and therefore the rest are unfused powder. So you can easily see where where is the unfused powder, or does the laser power is the laser power is enough to melt the material. And yeah, and also you can visualize the conductivity and also other density and other features. And also from the thermal state, you can change it to the melt pool view, and you can keep track of dynamic melt pool evolution. I think that's all for today. Thank you so much for attention.